And the answer to this is yes. There is, in fact, one beautiful formula which gives all of this in these special cases. And we almost know how to derive it. We almost know all the ingredients necessary to understand it. I have explained most of them. But now I can actually give you full disclosure, okay, and demystify all of these formulas. So here it goes. This is that general principle which I have been promising you from the beginning. The general principle I've been promising you from the beginning looks like this. But up to now, I was just saying it in a kind of a figurative way, sort of as a guiding principle, as a rough outline, because I never explained what kind of object this omega is, what is d omega, what does it mean to integrate over y over b of y, and so on. Also, technically speaking, I should put several integration signs on both sides. The number of integration signs should be the dimension of y here, and the number of integration signs should be the dimension of this one. But I will ignore that issue for now. Okay? And so now finally we can say what these objects are. Okay? And what these objects are, this omega, is what mathematicians call differential forms. Omega is a differential form. And this d is an operation on differential forms, which I explained last time. I explained in several examples on differential forms. And so now what I want to do is I want to explain one more time how you get all of these formulas from this single one, a very simple general formula. Okay? So the way it works is like this. Let me start in the case where in the left. I will explain it by example. So I will start with the leftmost column. In the leftmost column, omega, so d equal 1. And so d minus 1 is 0, right? We are integrating omega over the boundary. So the omega should be an object that we want to integrate over a d minus 1 dimensional domain. So in this case, omega is just a function. And in this case, this mysterious operation d is nothing mysterious. It's just a differential which we learned a long time ago. So what is it? Well, let's do different subcases. If n is equal to 1, it means it's a function in one variable. In this case, the differential is just f prime of x dx. And that's exactly what you integrate in the left upper corner, right there, f prime of x dx. Right? Let me show it. This is exactly the integral of df over this interval. And this you can think of as the integral over the boundary of this interval. So this formula works out. It does indeed look like a special case of this general principle, right? So we can check this box. The next case is when n is equal to 2, or let's do both 2 and 3. In this case, it's going to be df dx dx. Let's do it for n equal to 2, just to simplify matters. It's going to be df partial derivative with respect to x dx plus partial derivative with respect to y dy. And so we will be integrating. So here we'll be integrating this. Here we'll be integrating this. But this is exactly the integral of nabla f dot dr, which we have in the formula for d equal 1 n equal 2, right? Because what is nabla f? Nabla f is a vector field which has components derivative with respect to x, derivative with respect to y, and dr is also a vector which has components dx and dy. When I take line integral, I take a dot product. When I take this line integral, I have to take a dot product between this and this, right? What's the dot product between this and this? It's just this expression, which is nothing but the differential of f. So instead of writing this, we might as well write integral of df. Right? So again, in this case, we can rewrite this formula in a new way. We can write it as integral of df is equal to integral of f. Here over this curve, which by the way, I should say that here we have this orientation. And here we take it over the boundary of this. Again, what this integral is understood is just the difference of the values. Are you with me on this? Do you see what I mean? That this formula gives you this? Ask me if it's not clear. Okay? So next, so that's d equal 1. So d equal 1, we have now explained how to get from this general principle by making sense of the separation d. Here d is just differential function. Okay, so let's now go back let's go to the second column and let's look at this example. D equal to n equal 2. So in this case, d minus 1 is 1. The domain has dimension 2. The boundary has dimension 1. And let's look at the case when n is equal to 2 first. That's the case of Green's theorem, which is the upper corner over there. In this case, omega is going to be the following expression, p dx plus q dy, which is exactly what's written here. P dx plus q dy. Again, you could think of this as a line integral of the vector field with components p and q. But actually, when I wrote this down, I already wrote it in a way which we need. P dx plus q dy. So what is d omega in this case? So this is something I already explained in this case, and I also explained on Tuesday. I explained how to do this. But let's do it one more time to convince ourselves that this will give us that result. So by definition, you apply this in the same way as you apply to functions, because this is a function and this is dx. So you just apply it to this function and you multiply by dx. So by definition, d omega is dp dx plus dq dy. Let's write it in more detail. What is dp? That's dp dx plus dp dy. And then we have dx. You have to remember. Let me open the brackets and multiply them. And I have to put dy here. Dx here. So that's this term is given by the sum of this two. Plus I have dq dx dx plus dq dy, dy, dy. And again, let me open brackets, multiply them out. So I get dy. Okay, so that's d omega. But we have to remember the rules. And the rules are, the first rule is that if you have the same variable twice, dx dx, or dy dy, this is just plain 0. For an obvious reason, because what this should represent, what this kind of expression should represent is an elementary area. And if you take the area of a parallelogram where both sides go along the x direction, it means the parallelogram has collapsed and its area is 0. So that means that we have to get rid of this, and we have to get rid of this, which leaves us with two terms. But there's a second rule. The second rule is dx, let's write it like this, dy dx is equal to negative of dx dy. And I'll explain now in more detail what this means. We already talked about this, but I will explain one more time. If we do that, you see this comes with dx dy. So we get dq dx times dx dy. But this one comes with dy dx, and dy dx is negative of dx dy. So it's going to be minus dp dy. That's exactly the expression that we get in Green's theorem, right? So I can rewrite this formula as integral of d omega over d equals integral of omega over b of t. Well, this is just what's written here, because omega by definition is p dx plus q dy. And I have just explained that d omega is this. So that's why it's the same formula, okay? So I have also fit now this formula in this general principle, in the framework of this general principle. Let me comment now on this rule. Why dy dx is negative dx dy? In fact, the answer is best understood, this is best understood from in the framework of our calculation last time on Tuesday. On Tuesday we talked about this, and we saw, in the more general context of Stokes' theorem, and we saw that dx dy was by definition the Jacobian of xy over uv du dv. So d of xy, for more general surfaces, the meaning of dx dy is just that you parameterize your surface. So x and y become functions of some auxiliary parameters u and v. And then by definition, dx dy is just the Jacobian of this change of variables times du dv. But Jacobian is something we learned. Jacobian is given by some simple formula involving partial derivatives. I'm not going to recall what the formula is. What I need to recall is the fact that if you switch x and y, just by looking at the formula, you see right away that this is negative of d of y x over u, right? Because the Jacobian is given by a determinant of a 2 by 2 matrix. When you switch x and y, you switch the columns or the rows depending on how you write it. When you do that, you get a minus sign. That's just the way it is. The Jacobian has this property that if you switch the two variables, you get a minus sign. That's just the way it is, okay? And that's the reason why, since dx dy is this, so dy dx would be the same thing, but with this letter switch. That's why I get that dx dy is negative dy dx. So this might look a little strange. We are much more used to formulas like ab equals ba, rather than ab equals negative of ba. But in a sense, this is just as natural. This kind of formula is just as natural. This is a rule, for example, which we can find in many instances, like multiplication of numbers. We know that if you multiply two numbers, you get, it doesn't matter in which order you multiply them, you get the same answer, right? So that's called, we can say that this product is symmetric or commutative. Here's a slightly more non-trivial example. Suppose that a and b are vectors, and we are taking the dot product. And we've learned, and it's obvious from the formulas, that the dot product in this order is the same as the dot product in this order. So the dot product is symmetric. Right? The dot product is symmetric. But we've learned also another operation on vectors, namely the cross product. And cross product, for cross product, it's not true that a cross b is equal to b cross a. Instead, a cross b is minus b cross a. So if you know what cross product is, it shouldn't come as a surprise that sometimes operations that we do would be antisymmetrical like this. And in fact, the reason why we get a minus sign here, you can trace it all the way back to this antisymmetricity property of the cross product. Because here we talk about elementary areas, and cross product has to do with such, right? Cross product has to do with areas. The magnitude of the cross product is the area. So it's actually very closely related. This minus sign is very closely related to this minus sign. It is just an illusion that in nature, commutativity or symmetry property like this appears more often than this antisymmetry property. In fact, physicists learned a long time ago that amongst elementary particles, you have what's called bosons and fermions. And bosons are like, obey the rule like the dot product. They commute. But fermions obey this rule. Fermions anticommute. Fermion fields anticommute. And fermions are very important. We see fermions, fermions are all over the place. Right? An electron is a fermion. Okay? So don't tell electron that the way it behaves is unnatural. Okay? He'll laugh back at you, because if it were not like this, the atoms and the matter would not be stable. This property is just as important as the commutativity property that we also observe for bosons, like photons, for example. In fact, there is a higher type of symmetry which physicists study, it's called a mathematician study, which is called supersymmetry. And supersymmetry has to do with objects which obey both symmetry and antisymmetry properties like this. So you might have heard about the super collider, which just started, went back online like a week ago, which some people think is going to create some antimatter and destroy the world. To which I'm sure some physicists say, I wish. I mean, that would be really cool. It's not going to happen. But the question is, what can we find? And so one of the things which people hope they'll find is supersymmetry, which is a kind of higher type of symmetry mixing bosons and fermions. So, and this, when you analyze mathematically the equations which physicists would like to have confirmed or disproved, the kind of formulas that you see are precisely formulas like this. This kind of anticommutativity formula. So these formulas, I'm trying to say, is that these formulas are built in the very foundations of nature. So it's very natural, and it really comes up most naturally when you study integrals. When you study integrals, the rule is that dx dy is negative of dy dx. And this is the reason why in Green's theorem you actually get the minus sign, dq dx minus dp dy, and not the sum. You see, this is the reason. We trace it back to this anticommutativity property. Okay, so now this we've done. This confirms with this general principle. What about this? Stokes' theorem. This too, and this I explained last time. So I'm not going to do this calculation one more time, but let me just write it down. For for d equal 2, so we still have d equal 2 for y and d minus 1 equal 1 for the boundary. But now n is equal to 3, so we are in the realm of Stokes' theorem. In this case, omega will have an extra coefficient, which will be p dx plus q dy plus r dz. And this integral could be written as the integral of this omega. I didn't write this over d of n. Okay? For the same reason, I already explained it for integral in two-dimensional space. F dot dr is just p dx plus q dy plus r dz. The integral of this is the same as f dot dr, where f has components p, q, r. This is just a simple dot product. That's what the dot product gives you. It gives you this formula. What about d omega? D omega we calculated last time. Remember, it was a long and excruciating calculation, but it gave us precisely the curl. Right? It gave us precisely the curl. So d omega is actually going to be precisely the curl. Well, the integral of d omega, double integral of d omega, is precisely the double integral of curl. Last time. This is what we did last time. This is what we did last time. I'm not going to repeat this. And so, again, this formula, Stokes' formula, is a special case of the general principle. Okay? Any questions so far? And now we want to cast this last formula, the divergence theorem, also in the same way. So let's do that. Well, let me erase here. In the case of divergence theorem, we have d equals 3, so that the domain is three-dimensional, and the boundary of the domain is two-dimensional. Right? So what could it be? So the EDS, what does this look like? Well, in this case, omega is going to look like this. It's going to be a times dy dz plus b dz dx plus c dx dy. And last time I explained that this is precisely E dot ds. Last time. Where E is a vector field with components A, B, C. In other words, remember this definition, E dot ds is this integrals it's kind of a painful definition. It was very involved, and we had to do, it was a complicated formula which included RU cross RV. But last time I wrote out what RU cross RV is. I explained this in great detail. And when we look at what we got, and we use that formula for the Jacobians, involving Jacobians, then we actually ended up with this. I remember writing it right here. Okay? Just 2 days ago. So this we explained. So you see, and now we can actually appreciate this more. You see, a general omega is going to be a combination of all possible terms that you can write, involving these letters dx, dy, dz. Except, well, in this case, we should only have one of them for each segment. Only one. Why only one? Because we're going to integrate here over the boundary of a two-dimensional domain. So this had to be, we integrate that over one-dimensional boundary, one-dimensional object. And so dx, dy, dz should only occur once each time. What are the possibilities? Well, there's dx, there's dy, and there's dz. And we are allowed to multiply each of them by a function. That's how we get this expression, p dx plus p dy plus r dz. There's nothing else. But now we are supposed to be integrating this over two-dimensional object, over two-dimensional. So we should have 2 of those. We should have dx. What are the possibilities? There are 9 of them. There's like dx, 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 dy, dx, dz. There is dy, dx, dy, dy. You see what I mean? There are 9 possibilities because you have 3 choices for the first one, 3 choices for the second one. But in reality, there are only 3 choices, not 9. Why? Because first of all, dx, dx doesn't make sense. Well, it doesn't make sense, it's just 0. This is 0, dz, dz, 0. So 3 are gone. There are 6 remaining. But because of this property, anti-symmetricity property, dy dx is the same as negative of dx dy. So we shouldn't write it twice. That's why we only have dx dy here. If we had dy dx, we would just put it with negative sign and convert it into dx dy. So that's why those remaining 6 actually collapse to 3. dy dz, dz dx, and dx dy. Okay? So this is the most general expression which you can integrate over a two-dimensional domain. You can multiply each of those 3 guys by a function. And there you go. That's what you get. And I claim that actually the way we set everything up, integrating this object is the same as doing a surface integral of this vector field. It's just that we defined it as an integral of a vector field because it made sense for us, because if you think about the flow where E is actually a velocity vector field and the rate of flow is given by such an integral, rate of flow through a membrane would be given by this integral. But we could have set it up in a more abstract way by saying what could we possibly be integrating, and then you would see that what you could possibly be integrating is an expression like this. So there are different ways to define double integrals, but the result you get is the same. You either think about it as a flux or surface integral of a vector field with such components, or you simply say that this is an integral of this quantity, which is understood in the same way as before. For example, if you have this term, let's talk about this term. If you have this term, you just write for dx dy. You just write this expression. In other words, you parameterize your surface by auxiliary variables u and v, and you write dx dy like this.